Okay, so Sayantan, maybe you can already share your screen, and I will maybe say a few words before we start this webinar. So I'm happy that that there are already people connected. So this is, I think, the second webinar from the EURASIP, which is the European Society for Signal Processing. And as you may know, there are several technical committees in this society. I think that there are 9 or 10 of them. And this webinar is part of the BISA technical area committee, which means biomedical image and signal analytics. So before I give you the floor, maybe I can just say a few words about Sayantan, who did his master degree in fundamental physics. So he has a particular background because he did not start in computer science directly. So he did this in India, and then he also had a master degree in France, in Tours. And then he did his PhD student at the frontier between quantum mechanics and computational imaging in the University of Toulouse. And I was very happy to be one of his PhD advisors. And now he's a postdoc in more like medical imaging, working in quantitative acoustic microscopy under the supervision of Jonathan Mamou in Cornell Medicine University. So I think that that's all. So we are happy to have you here, Sayantan. So you have, like we said, 40 or 45 minutes to present. You can ask questions in the question and answers, which is on the bottom side of Zoom, or just by raising the hand, and I will give you the opportunity to ask questions. Okay, so go on, Sayantan. Thanks.
Yeah. Thank you, Adrian, for the introduction. Seems my sound should be fine.
We can hear you very well, yeah.
Okay, it's great. Okay, so yeah, good morning, so good afternoon, everyone. So I am Sayantan Dutta. So today I will present some of my works that I did during my PhD and my postdoc right now, that I'm doing right now. So let's start. So this will be the overview for my today's presentation. So I will briefly introduce what is the basics of quantum mechanics and image processing very briefly, and then propose few of my results, few of my methods. And at the end, in section 5, I will discuss what I'm doing currently right now during my postdoc. So let's start. So what is digital image and signal processing? So as we all know that at present time, we are surrounded by digital images in every devices, in our mobile phone, in our surveillance camera, in medical imaging, for example, MRI or ultrasound devices, and then satellite imaging in wireless communication. So we can see we are surrounded by all the digital devices in our everyday life. But during the data acquisition using some medical devices or some surveillance camera, or during the transmission process, so this data used to get distorted due to some external factor or maybe some internal noises. So this restoration of the high quality data from this distorted observation is one of the important tasks in digital and signal image processing. And this problem is known as the inverse problem. And mathematically, this problem is defined by this mathematical expression y equal to n of OX. So this is the inverse problem in digital signal and image processing, where y is the observed degraded version of the data, and x is the underlying hidden image or signal, that is the high quality information. Now here n is the effect of the noise. So the noise can be different type of noise. It can be signal dependent, independent. It can be an additive noise or a multiplicative noise, depending on the devices or the system. Now here O is the degradation operator. Now for different type of degradation operator, we can have different type of inverse problem. For example, if O is an identity operator, then the inverse problem becomes a denoising subproblem. So we have to solve the denoising problem. And for a blurring operator, if O is a blurring operator, then we have to tackle this deblurring or the deconvolution problem, where you have to restore the high quality information. For example, this fluorescent microscopy or this astronomical image that is captured by the James Webb Telescope. So you have to restore this blurry image to a deblurred image. And there is another one is called the subsam. If O is a product of subsampling and a blurring metric, then we have to solve the super resolution problem, where we have to increase the resolution of the image from a low quality observation. So these are different type of image problem. So there are other problem as well, but these are some more of the most popular or most challenging thing. And now there are different ways to tackle this. So here the main objective is that we have to restore this underlying X from the degraded observation Y. So that is the main objective. Now different techniques are available. For example, there is transform domain method, where we use this Fourier or wavelet decomposition for the denoising purposes. Then there is the spatial methods like this non-local mean, BM3D. And there is Gaussian method, where we use this map estimation for solving this inverse problem. And another technique is the variational method, where, for example, this alternating detection method of multiplier, where we iteratively solve this inverse problem by minimizing the cost function. So these are different techniques. So there are other possibility as well. And all these techniques are quite efficient for tackling this inverse problem. But in real life scenario, for example, in real life case, actually, the signal and images so the noise effect is signal or image dependent. So the traditional methods, these are particularly designed for Gaussian model, where this noise is random. But so these are not very efficient for a noise dependent model. And in our real life case, for example, in medical imaging or satellite imaging, so the image or signals are almost all the time dependent on the image or signal value. So in that scenario, so these standard methods are not very capable to tackle all these things. But there are other possibilities right now. For example, this machine learning technique is very popular. And also recently some works on this physics-based model, where we design an algorithm based on some principles of physics. Then there is graph signal processing. So these are some standard other techniques which are much efficient than the traditional method and gives a much better quality result. Now, in today's presentation, and my work are mainly concentrate on this physics-based model, particularly using the quantum physics, where I try to use these quantum physical principles for designing some algorithms. So this is the main objective of my work. So now how to design image or signal processing model using the principles of quantum mechanics. So before going into detail about my method, so just to see how we can implement the quantum mechanics into a image or signal processing domain. So there is one possibility is that we can design a quantum algorithm that is designed for quantum computers, and using this quantum logic gate, these qubits, everything, and then we can process our digital signal or quantum or classical signal using this quantum algorithm in a quantum computer. But there are some challenges. First of all, right now the scope of implementing an algorithm in quantum computer is very limited, because the quantum computers are not easily available. And another big challenge is that the devices we are using to acquire data or sending data, for example, this MRI machine or ultrasound machine or a satellite. So all these things are classical devices. So the data we have, these are classical. So these classical data we cannot use in a quantum computer. So that is a big challenge. But there is another possibility where we can design a classical algorithm that is inspired by the quantum mechanics. But so we design a classical algorithm inspired by the quantum mechanical principles and using this algorithm into a classical computer. So we are taking advantages of the quantum principles for improving a classical algorithm. So that is another possibility. So today's presentation, I will mostly focus on this aspect, how we can design a classical algorithm inspired by the quantum mechanical principles. But I just wanted to highlight that we also did some work on quantum algorithm aspect as well, where we try to propose a quantum algorithm for signal denoising. And so maybe right now we did some simulation on that on MATLAB, but in the future, when the quantum computers are easily available, we can try to implement this quantum algorithm into a quantum computer to process some signals as well. So today I will present my results. So I will mainly focus on this aspect, how to design a quantum-inspired algorithm for classical computer. Now, before going into the detailed method, just discuss very briefly what is the fundamental differences between a classical mechanics and a quantum mechanics. So this is a classical mechanical picture where we have a classical particle. This is a classical particle with energy E. And this is the potential surface, the V. So the particle is trapped under this potential and it's moving under this potential. Now, since the potential barrier at this point is much higher than the energy of the particle, so the particle will never able to cross this region and will never reach this place. So this particle will be trapped here forever and will oscillate in this region for infinite time if there is no damping effect. So this is the classical picture. Now in quantum mechanics, so the picture is completely different. So we have this wave particle duality of quantum particle. Now this is a short video. So here you can see, so a single photon is sending from this, emitting from this sender. So you can see that it's not like the classical particle. So when the single photon is traveling through the space, so it's not acting like a particle. So it's behaving like a wave. So it's propagating like a wave function, propagating like a wave. So these are the quantum wave function. So these wave functions give the probability of finding that quantum particle at some position in the space. And so here, this is the receiver. So here you can see this. So these bars actually represents the probability of finding the quantum particle on this receiver. So this just gives a probabilistic distribution. And we have this pattern. So this is one of the famous experiments in quantum physics in our modern history. So this is called the dual slit experiment. So it shows that the quantum particle can behave like a particle as well as a wave. So this is the wave particle duality nature of quantum mechanics. Now, in our case, so as we just see, so our wave function is defined by the psi, wave function psi. So this is the same potential surface V, but now we have a quantum particle with energy E. Now here we can see that so this is the wave function psi, and the probability of finding the quantum particle at some point in the space is given by the mod psi square. So this is the probability of finding the quantum particle at some point on the space. Now here you can see that although the energy level is much lower than the potential barrier here, like the classical picture, but the probability of finding the quantum particle in this point is not zero. It still have a non-zero probability here. So the quantum particle can tunnel through this potential barrier and can reach this place. So this is called the quantum tunneling effect. So this is also a unique property of quantum particles. Now these wave functions are actually solutions of the Schrodinger equation. So this is the Schrodinger equation where h is the Planck constant. It is the universal physical constant. M is the mass of the quantum particle. This is the nabla operator or the gradient operator. Psi is the wave function, and V is the potential surface under which the particle is moving, and E is the energy of the quantum particle. Now, with all this system, if we solve the Schrodinger equation, we get the wave function. Now, let's have a look of some particular wave function, how this wave function looks like, and how to solve this wave function particularly. Now, here I took a very simple example. You do not need to go into detailed math. I just show the basic equation. So just see there is it's called a particle in a box problem. So we have a potential V that is constant inside this potential box, and outside it is infinite. So the Schrodinger equation is only defined for this finite dimension. It's finite dimensional box. And the mass of the quantum particle is m. Now this is a one-dimension Schrodinger equation where V is constant for this length. So this is length L, let's say. Now we can just rearrange the equation. So, and then it's a very simple equation. So which gives the second order differential equation, which gives the wave solution. Even if you skip all these things, so you can see, so just highlight only these 2 points. So we can rewrite the Schrodinger equation in a different notion. And then if we solve the Schrodinger equation, it gives the wave solution. And so the wave function looks like this, where so this is the wave solution, you can see. And particularly in the phase term, you can see there is a factor called E minus V. So you can see that the frequency of the wave function depends on the this factor, so energy minus the potential. So the frequency of the wave function changes with different potential value and the energy value. So that is the very unique property of the wave function, and we want to exploit this property in our work. Now let's take some particular example. So this is one example of the wave solution where I solved the Schrodinger equation. This is the Schrodinger equation. I solved it for a different energy value for E0 to E3, from going low energy to high energy. And here V is the potential, it is constant. Now I solved the Schrodinger equation for different energy value, and we can see that the frequency of the wave function increases with the energy. So because E is increasing and V is constant, so we have a high frequency when we have a high energy value. But for a particular wave function, for example, for this wave function, the frequency of the wave function is fixed, just like the Fourier transformation. So there is a constant frequency. But now, if we have a potential with two different heights, so if the potential is not constant, so if we have a low potential region and high potential region, now if we solve the same Schrodinger equation with this new potential with low and high value, then we can see that the frequency of the wave function is not fixed anymore. So the frequency changes with the value of the potential because it depends on this factor, because V is not a constant in here. So here you can see we have a very high frequency region for low potential value, and we have very low frequency region for a high potential value. And that is the unique property of this wave function. That's why it is very adaptive with the system. And we want to exploit this adaptive nature while designing our algorithm. And now before going into that, so there is another quantum effect called the quantum localization effect. And this is mainly prominent when we have random noise in the system. For example, a noisy image in our case. So that means when we have a random fluctuation in the potential, if it is a random, there is random noise. So then the wave function is not spread over the whole space. Instead of that, the wave function actually localized into a particular region in the space. And here actually we are losing this potential dependent frequency, this factor, and that is called the quantum localization effect. And so these wave functions, localized wave function, are not very good for the image processing task. So we need to tackle this localization effect while designing image denoising algorithm first, let's say. So what is our basic idea? So our objective is to construct an adaptive basis using the solutions of the Schrodinger equation. That is our first objective. So for this, we rewrite the Schrodinger equation in an operator form in an eigenvalue problem, where H psi equal to E psi, where H is the Hamiltonian operator. And where I just told this is the nabla operator, the gradient operator, and V is the potential. So here our idea is to replace the potential V by the image pixels value. So we are using the image pixels as a potential for our system. And now since images are discrete in nature, so we discretize the Hamiltonian, and we have the discretized Hamiltonian like this. So where xi represents the pixels value for every individual pixel. Now we construct the Hamiltonian operator, and then we calculate the set of eigenvectors of the corresponding of the Hamiltonian operator H, and this set of eigenvectors gives us the adaptive transformation, and we use this adaptive transformation for the image decomposition. So just like linear filtering. So instead of using a Fourier transformation, we are using this adaptive transformation for the filtering of the image or the signal. So that is our objective. Now let's have a look how these wave functions looks like in presence of noise and in presence and without the noise. So for this, I choose a image where half of the image is contaminated with noise, and I extract two patches. You can see the patterns are more or less similar. Where this is the clean patch, this is the noisy patch, and here I plot the pixel value in the z direction. So you can see that the high pixel value represents the higher value in the z direction. So it looks like a 3D it looks like the 2D surface in the 3-dimensional plot. So this image. And you can see there are many hills and valleys like this. So we have high potential region and low potential region. So actually we are using this image patch as a potential in our Hamiltonian or in our Schrodinger equation. And we are assuming that there is an imaginary quantum particle. That quantum particle is moving under this potential surface. So it's trapped in this potential surface. And so there are many hills and valleys you can see. So this is the clean and this is the noisy one. Now, if we solve the Schrodinger equation for an energy level E, same energy level for these two cases, and we get the respective wave function. So this is the wave function for the clean, this is for the noisy. This is the 2D contour plot. This is the 3-dimensional plot. This is the 2D contour plot. Now, for the clean case, you can see the wave function uses different level of frequency to probe the space. So the frequency is not fixed, as I just told before. So that is the nature of the adaptive nature. Particularly, if we look at the center, we have a very low frequency region, and that is associated with the high pixel value or the high potential value. On the other hand, these two sides here, the frequency is very high of the wave function of the frequency of the wave function, and this is associated with this low pixel value. So you can see that the wave function is using different level of frequency to probe different region in the image, different pixel value. So that is the adaptive nature. But in presence of localized wave function, in presence of noise, so you can see that the wave function loses this adaptive nature. So the wave function is not spread over the whole space. So the main concentration only a particular in a region. So that is because of the quantum localization effect. So this is a very, so these wave functions are not very good for handling the denoising task or the filtering task. So let's see an example with this localized wave function. So this is a denoising with the localized wave function. So this is the clean image. This is the noisy image. And using this noisy image, as I just told, so we construct the Hamiltonian and then compute the respective set of eigenvectors using this noisy image. And so this is one such example of the wave function. As I just told, that the wave function is localized into a particular region, so it's not spread over the whole space. So we are losing the frequency dependence on the pixel value. The frequency here does not depend on the pixel value. And now, if we use this localized wave function for the image decomposition, and this is the result, so you can see that the result is not very good with this localized wave function. So we have to remove this localization effect. So for this, we did a small trick. So first, we smooth the image. So let's say this is a noisy image Y. And we compute a smooth version using a Gaussian filter, a low-pass filter. As we compute a smooth version of the image Y, and we get the YB. And then we construct the Hamiltonian operator using this smooth version YB. And from this Hamiltonian operator using YB, we calculate the set of eigenvectors. And this set of eigenvectors gives us the adaptive transformation or the adaptive basis. Now, when the adaptive basis is done, when it's constructed, we use the original noisy image Y and project on this adaptive basis to calculate the projection coefficient. So we are not using the smooth version. We are using the original noisy image and computing the projection coefficient. And then we perform the standard soft thresholding and do the inverse transformation and get the denoised image. So that is the denoising pipeline in our case. So here, the initial smoothing is done just to compute the eigenvectors. I just wanted to highlight that. And so this smoothing is done just to remove this localization effect, because we observed that the localized wave function are not very good for image denoising tasks. So just to remove this localization effect, we perform initial smoothing just to compute the set of eigenvectors, then use the original noisy image and project it on the adaptive basis to compute the projection coefficient. Now here I show a few results for signal and image denoising task. So these are some synthetic images, and this is the standard Lena image that I used. So this is our method called QAB, quantum adaptive basis, and I compared with total variation. We also compared with Fourier based denoising and wavelet denoising, then some graph signal processing method, dictionary learning. And we observed that our method is quite well. perform quite well compared to this method. And here we also observe that when we remove this localization effect from the wave function, so you can see that it improves the quality of the result in a significant way. Unlike compared to the localized wave function, we have a much better image denoising result. So you can see that the trick is actually useful in this aspect. So our method works quite well, but there are some big challenges. So although it is a very good flexible with the noise statistics, so yeah, I just wanted to highlight that. So this method is it's very efficient for signal dependent and signal independent noise model. So you can easily apply the same method for Gaussian, Poissonian, speckle denoising, and it gives relatively comparable good result compared to standard state-of-the-art method. But there are some big challenges. First, the high computational cost of the eigenvectors from the Hamiltonian operator, because if we have a large image of, let's say it is a size n by n, then the respective Hamiltonian operator will be of size n square by n square. So the respective computational cost is exponentially increases with the size of the image. So that is a very big challenge. And also, if we use a block-wise technique, so if we divide the image into small blocks just to escape this localization effect, just to escape this computational problem, but these different blocks in the image, they are processing independently. We are processing them independently, so there is no relation between them. So we are but in the standard natural images are generally dependent on some the local structural similarity. We can always find some local similarity in a local image neighborhood. So we are not taking into account this type of effect in this algorithm right now. And finally, the initial smoothing of the to escape from the localization effect. So there is also a big challenge, because so we have to tune the parameter of the Gaussian smoothing, and then it can create some extra artifact. So there can be some other effect as well if we do not tune the parameter properly. So you can see there are many external challenges as well. Now, to resolve all this issue, we further generalizes our method to a quantum many-body theory, and where we can efficiently solve all these limitations, and we can solve this initial smoothing and the localization problem as well using the quantum many-body theory. So in the next section, I will move to that. So how to design a signal and image processing algorithm by using a quantum many-body theory. So till now, I was discussing about a single particle-based theory. So where we have a Hamiltonian H. So this is a single particle-based Hamiltonian. So that means in our system, there is only one quantum particle. And so this, and we, for the imaging point of view, we replace this potential V by the image pixels value. And we construct the Hamiltonian operator and adaptive transformation, everything. So this is the one body quantum mechanical picture. Now, if we have a many body system, that means there is more than one quantum particle. So particle A, B, C, let's say. Then, so this is the Schrodinger equation for the particle A. Now we have the similar type of Schrodinger equation for all the particles, the particle B, C, everything. Now in this many body system, there is a particle-to-particle interaction takes place, because they are neighboring particles, so they will interact between them. And as a consequence, in the Hamiltonian operator, there will be an extra term that is called the interaction term. And so this interaction term, from the imaging point of view, so we divide the image into small patches, where every individual patch acts like behave like a single particle quantum theory, single particle based quantum system. And so, and the local image neighborhood, in a local image neighborhood, they interact between them and show some interaction. And by using this interaction, we can preserve the structural similarity in a local image neighborhood. So that is the idea. So when we divide the image into small patches, while every individual patch acts like a single particle based quantum system, so the whole many body quantum system can efficiently preserve the structural similarity in the local image neighborhood. So that is the idea. So here you can see we have a modified Hamiltonian with the interaction term, and from the modified Hamiltonian, then the process is same. So we calculate the eigenvectors and then compute the adaptive transformation and do the thresholding as we did before. So here, just to highlight, so we'll get different Hamiltonian for different image patches. because we will get different type of interaction when we choose different image patches, different local, different neighborhood. So depending on that, the interaction term changes, and we will get different Hamiltonian operator for different patch. Now, so this is the diagram. This is how we calculate the interaction. So first, let's say we want to denoise this target patch, and centering this target patch, we choose the search window, and then we extract all the patches from the search window, and here the patches can overlap. And so this is the target patch, this is the neighboring patches. Then we calculate the interaction between them, and then this is the interaction term. And so this, and then combine all the interactions, we get the total interaction. And this is the initial potential. And combining these two, we get the new modified effective potential. And this is the effective potential for this target patch. And we use this effective potential in the Hamiltonian operator, and then calculate the respective adaptive transformation, and then do the filtering. And this adaptive transformation is customized for this target patch only. And we do the same process for all the patches in the image for the denoising task. Now, this is the modified Hamiltonian that we get, where, so the first, this V is the same. We use the noisy patch as a potential, it's the same thing. And here I is the interaction between the patches. So this is the modified Hamiltonian operator. Now, using that, we can, when we use this interaction, as I told, we can efficiently preserve the structural similarity. And also, since we are working on small patches, so the computational cost is also significantly low compared to the single particle based, the first first algorithm that we proposed. Now we study different type of denoising problem. For example, this is a Poissonian denoising result. We also study the Gaussian denoising and other type of image noises. And here I compared with some method. This is the non-local mean, which is designed for the Poissonian denoising problem. And this is the BM3D customized for Poissonian. And this is our single particle based theory. And this is our our result. So our method is called the DQI. And if we compare the single particle based theory and this many body theory, we can see there is a significant improvement in terms of PSNR and SSIM. And this is because of the preserving the preservation of the structural similarity using this interaction term. And also, if we compare with the other methods, we can get comparable result and sometimes quite good result by using our method. And so these are some standard denoising technique. And so another highlight is that we do not need to change our model depending on the noise statistics. We can use the same algorithm for different noise statistics. It is equally efficient for Gaussian, Poissonian, speckle. Now, we also apply our method for the medical ultrasound image. In medical devices, when we acquire the ultrasound images, some ultrasound probe. So because we in the ultrasound sender, this is the ultrasound probe. So it actually emits the ultrasound wave, and it's move through our body and then hit in one of the organ in our body. That is the part the focus is, and then the reflection goes back to the receiver, and during this transmission and the receiving process, because of the constructive and destructive interference, so there is a speckle pattern generated inside the ultrasound image. And as a consequence, we can see this granular pattern in the image, and which significantly degrade the image quality. So in ultrasound devices, one of the important tasks is that the respeckling. So we have to remove the speckle to get a high quality image. And so this is very efficient. This is very important for the better medical diagnosis. So we apply our method for this ultrasound image despeckling problem. And this is the result. So here we have a cancerous thyroid image. So this is the cancerous thyroid ultrasound image, where you can see there is a significant speckle is there. And these are the different methods that I compared. So anisotropic diffusion, Lee filtering, and non-local mean. And this is our proposed method. And we compare the contrast to noise ratio and the resolution loss. And our method actually gives a good balance between the contrast and the resolution loss. So it gives the better contrast while having a less spatial resolution loss compared to the other standard techniques. So for example, so here at the top, I show one profile from all this line. So here the red line is actually our method, and this purple line is the non-local mean, and the green one is the leaf filter, and the blue one is the anisotropic diffusion. So the non-local mean gives the best contrast to noise ratio, but the resolution loss is also much higher. Whereas the anisotropic diffusion, the resolution loss is much low, but the contrast to noise ratio is also very low. And so it is also visible from this figure. Here you can see that the red line, so the gradient of this red line is much higher compared to the non-local mean. So it shows that the resolution loss is much lower compared to our proposed case, while getting a better spatial contrast. So you can see that our method is also works quite well for real medical imaging application for ultrasound images. And so this is the schematic diagram that I proposed of our DeQuib algorithm. So I just wanted to highlight again. So we first did we have a noisy image. Then we apply a patch extracted operator and extract all the patches, then compute the interaction between these patches in a local image neighborhood, and which is multiplied by a proportionality constant P. So P is the proportionality constant that actually regulates how much interaction will be there. And then we calculate construct the Hamiltonian operator by combining the nabla operator, the interaction, and the original noisy patch. And from the Hamiltonian, we get the adaptive basis for each individual patch. And then we project the original noisy patch on this adaptive basis, projection coefficient we get, then perform some thresholding. For our case, soft thresholding right now we are doing. Then we restore the thresholded coefficient, and then do the inverse transformation, and then we restore all the patches into their original location. So that is the schematic diagram of our work. Now here we have mainly three hyperparameters. One is this proportionality constant that regulates the interaction. Then the nabla operator. Here we have this h squared by 2m, the Planck constant, and the mass of the quantum particle, this factor. And then finally the thresholding. So the thresholding factor. So these are the three main hyperparameters in our case. Now, in our previous work, we try to tune them based on some physical intuitions, and we did some statistical study. But these parameters are fixed for all the patches in an image and does not vary in a patch-wise fashion. But if we think about the interaction or this Hamiltonian operator, so maybe depending on this local image neighborhood, so we should define different parameter value, because this different image pattern can have a different effect in the interaction. So, but in our case right now, that is not present. And also, if we look at the adaptive basis vector, when we are using a same parameter for all the patches, so that means we are using a same imaginary quantum particle with same mass is present in the system, but it can be different quantum particle, different type of quantum particle, so present in different patches in the image, and they can interact differently between them. So this type of things limitation is there. So it is impossible to tune them in a manual task. We cannot do it manually. So for this, we further converted our method into a deep learning based CNN based architecture, where we can solve this parameter tuning problem quite efficiently while preserving the quantum based idea. So that is the next section of my talk, where I will just explain how we can design a deep learning model using this quantum based principle. Now, so this is the schematic diagram that I proposed, and this is the respective unfolded model based on our DeQuib principle. So here our basic idea is to replace the patch-based computation with fixed weights by a convolution layer. So we replace all the matrix multiplication, but we have a patch-based computation, by the convolution layers. And then we trained our model in a supervised way. And when we do this, you replace this matrix multiplication by a convolution layer. So by doing that, we calculate the interaction, and then we construct the Hamiltonian kernel C2. So instead of computing the adaptive basis in a traditional way, we are not solving the eigenvalue problem. Instead of that, we are defining a convolution kernel C2, depending on the same principle, using the gradient operator, the interaction, everything. And using this kernel C2 for the next convolution layer to computing the projection coefficient. Now, this is the diagram. So we are starting with a noisy patch, noisy image, then we extract all the patches. So it's the same algorithm that I show. And just to highlight that, so this is the interaction. For computing the interaction, we perform this convolution layer with the kernel C1, and then use this interaction I and this nabla operator and this original noisy patch to compute the second kernel C2, where we have this learnable parameter a squared by 2m. And using this C2, we are using this C2 in the next convolution layer for computing the projection coefficient. And then for the thresholding, we use ReLU, and then another one is for the inverse transformation. So that is the basic idea. And we trained our model in different images, and it works quite well for the denoising task. And also we tried the super resolution deconvolution. Now here I show some example for the ultrasound image resolution enhancement task, where we took some human anatomy images, and this is the respective speckle version, which are generated by using the Simon's toolbox. And then we trained our model using this pair of images in a supervised way. And here I compare with the baseline DeQuib algorithm, and this is our proposed algorithm. And we can see that compared to the DeQuib algorithm, our proposed this deep learning model is significantly better. It's much better and much close to the original noisy patch, original noisy image. So this is because of the using of different parameter value for different image pixels. So, and we further study the same model for the cardiac ultrasound image enhancement problem. So this is the cardiac data. So you can see this is the human real cardiac data. It's acquired during the regular health checkup from a patient. So you can see there is a significant speckle is present, and also the resolution is not good. We try to enhance the image by using our method. So this is the enhanced version. So you can see the speckle is significantly removed from the image, where the resolution is significantly improved. Where you can clearly see the structure of the heart quite efficiently, how it works. And there is another example. This is from another patient. So you can see that the speckle is significantly present here, but we can significantly remove the speckle from this low resolution data, from the low quality data, and the resolution is significantly enhanced by using this deep unfolded model. So this is the basic idea in this deep unfolded idea. Now, right now, let's move to what I'm doing during my postdoc right now at Cornell. So where I'm trying to enhance the resolution of the parameter maps of the quantitative acoustic microscope. So what is quantitative acoustic microscopy? So this QAM, or the quantitative acoustic microscopy, it uses very high frequency ultrasound waves with a more than 200 megahertz frequency. And this is 2 orders of magnitude than the standard conventional medical ultrasound devices that we use. And these high frequency ultrasound devices, using that, we scan some small, very thin soft tissue, for example, this lymph node sample. So these are 6 micron thickness. And after scanning that, we can get a 2D acoustic parameter maps. So acoustic parameter maps means we get the different acoustical property like the speed of sound and the acoustic impedance, attenuation. And from that, we can calculate the mechanical properties of the soft tissue like bulk modulus, mass density. So these are some examples. This is the attenuation of this eye sample. So this is a small section of the eye, and this is the bulk modulus of the eye. And compared to the traditional optical microscopy technique, so this is the optical microscopy. So these acoustic properties, these acoustic parameter maps actually gives complementary information compared to the standard technique, standard optical microscopy imaging. So now this quantitative acoustic microscopy, these are successfully implemented in different type of medical diagnosis, for example, human ocular tissue characterization, then liver diseases and the myopia study. So these are significantly quite successful in this different type of problem. But the spatial resolution of the acoustic microscopy is limited for some short-term medical application. Now, one possible way is that we can increase the center frequency. We can increase the frequency of the transducer to get a higher quality data, to improve the spatial resolution. But when we increase the frequency, so there is some external challenges. For example, if we want to increase the frequency, so we have to spend much more money to improve the hardware part, because the cost of the transducer, the electronics significantly increases with a higher center frequency. And also the environmental challenges also exponentially increases, because as we increase the center frequency, it becomes more and more sensitive with a small vibration and temperature difference of the system. So these are some very complicated challenges at this moment if you want to increase the center frequency. Now, for implementing this QAM system into a real medical application, we need a robust system that is low cost, user-friendly, and gives a better spatial resolution. Now, right now, from the hardware point of view, there is a significant limitation. But one possible way is that we can use a post-processing technique to improve the resolution of the parameter maps. And here, so that is the objective in this domain. Right now, I'm working. Now, so as I just told, the image formation model, it is the same image formation model. Here we can define the super resolution model, where Y is the observed parameter map, and X is the underlying high resolution parameter map. And so this is a yield post-inverse problem. And we can rewrite the problem using the map estimation, and where we get this the optimization of the loss function with a regularization. So this regularization depends on some prior hypothesis like the sparsity or the speech-wide smoothness, all these things. And then this cost function we can solve using different technique. For example, here I am using this ADMM, or the alternate integration method of multiplier, where we rewrite the problem into a constraint-based problem. So I'm not going into detail how we did, so just very briefly I'm just explaining. And then finally we reach this 3 iterative step of the ADMM, where the first step is the denoising subproblem. So where we are trying to denoise this xk plus zk with the help of the prior function. So you can see, so the first denoising subproblem involves the prior function, and this depends on some prior hypothesis of the image. And the second problem is the inversion subproblem, where we try to invert the effect of the degradation at the blurring operator. And the third is the update of the Lagrangian multiplier. Now, as I just told, let's have a look of this denoising subproblem first. So this is the denoising subproblem. So you can see, so we have to choose some prior hypothesis about the underlying image. And this is for real medical imaging application. So this is a very challenging task, because we don't know about the underlying properties of the image, of the parameter maps in our case. So we cannot use the standard sparsity or the local smoothness property here for the restoration task. Now, very recently, a new idea called the regularization by denoising that is proposed, where we do not need to choose any explicit prior function. Instead of that, we can define a rate prior, that is called the rate prior, external prior function, by using an external denoiser D. So that is the state-of-the-art denoiser like BM3D or any wavelet denoising, any denoising. External denoiser, we can use it to define a prior, and then we can solve this denoising subproblem using this external denoiser. Now, there are still some challenges, because most of the external denoiser are designed for handling Gaussian problem, as I just told at the beginning. But our real medical images, so the noise may not be Gaussian, it can be mixed, or it can be some signal dependent. Most of the time it is like that. So there is a limitation with that, with the standard denoising technique. So we use our decouped denoiser that I proposed beginning as a rate prior for solving this restoration task. Now we propose these 3 iterative steps. So first, it is the denoising subproblem. using our Dequip denoiser. Then we use a closed form solution for solving the inversion problem. And then third is the update of the Lagrangian multiplier. So this is our proposed algorithm. And we also study the fixed point convergence, and we observe that if Dequip satisfy all these 5 conditions, I'm not going into detail about that, but if this condition satisfied, so then we observe that our ADM algorithm will converge to a fixed point. And our work is already accepted for the ISB, so I'm going to present in next 2 weeks. And another extended version is submitted, it's under review, so hopefully we'll receive the response very soon. Now this is our proposed algorithm. Now let's have a look about the result. Okay, so before how we acquire the data. So this is our QAM setup that we used here at Cornell. So this is this acoustic microscopy system, and this is the transducer, and where this thin glass plate is placed here under the transducer. And so this is the glass plate sample. So we scanned a small region in the glass plate, and using 2 different ultrasound transducer at 250 megahertz and 500 megahertz with 2 different resolution. And we scanned 9 lymph node sample from human tissues, cancerous, non-cancerous. And then there is a standard technique for image processing to calculate the parameter maps. So we did that. Now let's have a look of the result. So this is the histology image, and this is the acoustic impedance map at 2 different frequency. So this is the 250 megahertz, this is the 500 megahertz, and this is our proposed result. And I compare with 2 different standard technique. One is total variation based analytical method, super resolution technique, and this is the RAID with BM3D. So this is the Gaussian based model, the Gaussian based BM3D model, and this is our proposed adaptive model. Now for a better comparison, I just zoomed in to this section from the image. And this is a zoomed in version. So you can see in the 250 megahertz data, so there is a very blurry information. So there is not much information is there. Compared to our proposed method, we can see that the finer details. So there is this blurry information significantly recovered from this blurry observation using our proposed Dequip algorithm. The BM3D is also good, but in the next section we compare some quantitative metrics, and you will see that our method is much efficient. And so it is also true for the 500 megahertz data, where you can see this 500 megahertz acoustic impedance. So there are some information much better than the 250 megahertz. But when we try to restore this image from this observation, we can recover much more details in the acoustic impedance map. So you can see that our proposed Dequip RAID algorithm works quite efficiently in this acoustic impedance map, and particularly this acoustic microscopy system for the resolution enhancement. And we calculate the spatial resolution quantitatively by using the normalized autocorrelation function for a quantitative metric. So this is the radial leveraging of the autocorrelation function, and from that we get the explicit the resolution. For the 250, the acquired data resolution is 7.6 micron, where we go up to, using our method, 4.62. Compared to the BM3D is much better, you can see. And also with 500, the initial was 3.55, where our proposed result is 2.52. Compared to the BM3D and total variation, you can see there is a significant improvement, and for the improvement of the spatial resolution. And so this is the main observation right now, and we are trying to improve the result right now in a 3D, in a 3D RF data space. And currently we are working on this 3D RF data. So this is the most of the work that I wanted to present today. So there are many things to be done at the future, actually. So first of all, we can try to design some complex, this quantum-based deep neural network and train in a different way for unsupervised training. So that is one obvious perspective. Then we can try to see the graph signal processing, the relation between graph signal processing and our quantum-based method, because there can be a similarity between these 2 techniques. So you have to explore this aspect as well. Then we can try to use the quantum harmonic oscillator. Actually, this is a more advanced of the many-body theory, where every individual pixel acts like a single particle-based quantum system. So not like a whole patch, but every individual pixel. So this is a more advanced version of the generalized quantum theory. And then we can try to use the time-dependent Schrodinger equation, because here we are mainly using the time-independent Schrodinger model. But this time-dependent Schrodinger model can be useful for processing periodic signal, particularly, for example, let's say the video, and we can see how the wave function evolve with the time. So these type of things can be studied. And another one is the quantum computing. We did some work, but there are many things can be done in the future. And there are other possibilities as well. Just wanted to highlight one, because so here there is one paper that is published in 2 years ago, where they use this adaptive transformation for the hydrocarbon detection. So I just wanted to highlight that. So it's not limited to some image processing or some traditional medical imaging. So it can be used in different imaging modality or different domain as well. So that's all mostly. And finally, I just wanted to thank to my supervisors, Adrian Bassarov, Bathon, George Joy, Jenny Kwame, and Jonathan Mamu. So I don't have an image for them with me. And this is the one image with Adrian and Jonathan last year during my wedding. And I want to thank them. So this is my papers and codes are available here. If you have any questions, so I'm happy to answer your questions.
Okay, thank you, Sayantan, and thank you for recalling me these very nice souvenirs from India. I don't know if there are no questions for the moment in the QA text box. If someone has questions, you can just turn on your microphone. No questions. I hope that people can turn on the microphone if they want to ask questions. Okay, anyway, we are just on time, so it's exactly 1 hour.
Yeah.
So I think that in this case, we can thank you again, Sayantan, for the very nice presentation, and hopefully this second webinar of EURASIP was a success, and looking forward for other future webinars.
Yeah.
So thanks all for joining, and I think that the webinar was recorded, and I guess it will be available on the EURASIP website very soon.
Yeah, and also if the attendees want to ask question in the future, they can contact me. I will be happy to explain the idea if they have any confusion. So it's okay. We can discuss later as well with them.
Perfect. And they can also find you in Athens in 2 weeks. Okay, thank you so much. Goodbye, everyone.
Yeah, thank you.